charged particles with angular momentum have magnetic moments. So, classically, an electron orbiting, here's our electron and here's our classical orbit for this electron, with some velocity v, so at any given point on the orbit here, a vector velocity v, in a circular orbit of radius r, as, for example, we write down in the Bohr model of a hydrogen atom, although we know that particular model is not correct. But for this electron hypothetically orbiting in a classical sense, then it would have an angular momentum of magnitude L equal to the mass times the velocity times the radius here. That's a standard classical result for the angular momentum of a particle orbiting in a circular orbit here like this. We can also write an angular momentum as a vector. Again, classically, the standard definition is to say that the angular momentum vector is r vector cross-producted with p, and classically the momentum p is just m naught, the mass here of the electron, times the vector v. Now, the electron takes a time 2 pi r over v to complete an orbit. 2 pi r is the circumference of the circle, and it's going at velocity v, so it takes at a time 2 pi r over v to complete an orbit. And so per second, it completes v over 2 pi r orbits. So v over 2 pi r orbits per second. So the amount of charge passing any given point on this loop here per second is simply the current minus E, that's the charge, times the number of orbits completed per second. So that's the number of times the electron passes any given point. So we get a current like this. Now, we define magnetic dipole or magnetic dipole moment, which we can call mu d, in ordinary classical electromagnetism, a quantity that is essentially the strength of a magnet. For any closed loop, the magnetic dipole moment would be the current times the area. The current loop here, corresponding to our orbit, has an area pi r squared, and we've deduced our current. So with this area, the orbiting electron classically has a magnetic dipole moment, current times area, equal to minus E VR over 2, which is the same thing, if we check back our definition for L, as minus E L over 2 m naught, where L was the angular momentum magnitude. Or in vector form, we can define a vector magnetic dipole moment, so it has a direction to it, as minus E over 2 r cross V. So instead of minus E VR over 2 here, we can choose to define the magnetic dipole moment like this. And that would correspond to minus E over 2 m naught times the angular momentum here. With this magnetic dipole moment as a vector pointing towards us in this diagram by the right-hand rule of the vector cross product. Now, if we apply a magnetic field, classically the energy of an object with a magnetic dipole moment, mu d, changes by an amount that is minus mu d dot producted into the magnetic field. This is like thinking of the energy of a little magnet in the presence of a magnetic field. It's obviously proportional to the magnetic field, and it will have a dot product sense to it because this energy will be largest when the magnetic dipole moment and the magnetic field are lined up, largest in magnitude that is. And what direction the energy is in depends how the north and south poles, as it were, of this magnetic dipole little magnet are oriented with respect to the field. With conventional definitions, we end up with a minus sign in here. Now, applying B along the z direction to a hydrogen atom would actually force the z direction to be the special direction in the hydrogen atom. We could check that out. We won't do the quantum mechanical version of this problem here. And that would mean that round about the z direction, we would expect the angular momentum to be quantized with values m h bar, where m is an integer. It's the m quantum number of the hydrogen atom, which incidentally is really called the magnetic quantum number. So we're not solving this quantum mechanical problem here, but this is what would happen if we did, at least neglecting spin for the moment. Applying the B along the z direction would force the z direction to be a special one, and that would mean that the angular momentum would be quantized round about the z direction with eigenvalues m h bar. Or in vector form here, we could write that angular momentum as m h bar times a unit vector in the z direction. This is not an operator here, this is a unit vector. And this integer m, we remember, for the hydrogen atom goes in integer steps from minus L to plus L. So continuing with a semi-classical view here, a semi-classical model for the moment, with a vector angular momentum m times h bar times z hat, unit vector in the z direction, m is our integer here. Our classical formula would give us a magnetic dipole moment like this. So we would expect magnetic moments for these electron orbits of this kind here. This is just minus E times L over 2m naught. So here is our angular momentum here, m h bar z, so that's the equivalent of the L. And that corresponds to the following formula here, where we define something called the Bohr magneton with this formula. It's just a convenient unit for talking about magnetic dipole moments. So, applying a magnetic field B, we would therefore expect energy changes for these states, at least in this semi-classical view of our problem here. And we would expect those energy changes to be of the following form. Here's our magnetic dipole moment. Hence, our energy changes would be m, our integer, mu b times the Bohr magneton times the magnitude of the magnetic field. So, in a hydrogen atom, we might expect an applied magnetic field to split the two L plus 1 degenerate energy levels into two L plus 1 different energies, the Zeeman effect. And this is, roughly speaking, what does happen in a hydrogen atom if we solve this problem properly in a quantum mechanical sense. So a p state, L equals 1, would split into 3 levels. Now, as I said, we should do this calculation quantum mechanically, and we could do that. We would use, for example, degenerate perturbation theory, and we would be able to solve this kind of a problem, neglecting spin for the moment, and looking at the so-called Zeeman splitting of these levels in the hydrogen atom as we applied magnetic field. And formally, our perturbing Hamiltonian operator would just be this energy term here that we worked out. But now we would be using the angular momentum operator, at least in this semi-classical first attempt at this problem. But the result of a fully quantum mechanical version here with this version of the perturbing Hamiltonian would in fact be the same as we would deduce semi-classically by our argument above. Again, neglecting spin. Magnetic moments of particles also lead to deflections in non-uniform magnetic fields, as in the Stern-Gerlach experiment, for example. For particles with arbitrary initial values of m, repeating the experiment many times should lead to 2L plus 1 different deflection angles emerging. Hence, a Zeeman splitting, or a Stern-Gerlach experiment, should show how many different values of the z component of the angular momentum are allowed. What happens for an electron itself in a magnetic field, especially when it has no orbital angular momentum? How many different values of the z component of the angular momentum do we see? The answer, surprisingly, is 2. But on the arguments we've been discussing here, that does not seem to make sense. If we look at angular momentum in the sense we considered it for the hydrogen atom, with 2L plus 1 different possible values of angular momentum round the z direction, there is no integer value of L that will give us just 2 different possible values. L equal to 0 gives us one possible value of angular momentum around z, which would be 0. L equal to 1 gives us 3 possible values of angular momentum around z. How can we possibly get two values showing up in experiments, such as the Stern-Gerlach experiment or some Zeeman splitting experiment. This paradox is resolved by the electron spin, but as we'll discuss in the next section, it does mean that spin is not represented by a spatial function in the conventional sense.